All right, folks, welcome back for the afternoon session of our day. Is it day 5 of our bootcamp? Today, in the morning, we covered CLIP and BLIP. Just to recap, in a very, very quick recap, CLIP was foundational in the sense that it opened the door to multimodal learning. Right. And it was a group of breakthroughs that made quite a difference. We followed that with BLIP. A BLIP was not just about understanding images and therefore could be used for retrieval, right, search, but you could, and of course you could use CLIP for zero-shot classification and so forth, like as you can do. Those were the good things with CLIP, but it was not generative. Right? Classification is still a discriminative task. Retrieval, it was good at. It is still good at. It's used quite heavily. But today, then we went to BLIP. BLIP had a 4-pillar architecture, if you remember. The first 2 pillars were basically CLIP. The left 2 pillars, you had an item text contrastive loss. Then you had an item text matching loss, the standard entropy loss, cross entropy loss kind of thing. And then you had the standard decoder loss. You want to produce certain text, and what's the loss associated with that? That was the architecture. It was a 4-pillar thing. Now, and I won't rehash the 4 pillars, but that's what it was. What BLIP-2 comes from, I think, the same group of people, Salesforce. They had an interesting epiphany. They basically said that, see, the decoder, why are we training the decoder? These days, the generative tasks are done very well by what? What is good at generation these days?
Thanks.
The LLMs. Right? So let's replace the decoder with the LLM. It's really good at it. Right? Now, encoder also, let's not train the encoder unnecessarily. CLIP and all of these things have become very good at it. Right? Let's just assume that they will do the encoding. So what you do is you take 2 pieces, the 2 pillars, encoder pillar and the decoder pillar, the first image encoder pillar and the whole decoder pillar, you just borrow. Borrow means you take pre-trained models and you freeze it. Freeze means the weights cannot change. There is no learning that they can do. And then the inner 2 pillars you call are the only 2 pillars that can train. Are we together? And it becomes the glue, and they change the architecture a little bit and we'll talk about it, but it becomes the inner glue, right, between an image encoder and a full large language model to decode. Are we together? So what you do is, and as this picture shows, if you pay attention to this picture, whenever you see this snowflake picture, it means that these models are frozen. You borrow a frozen image encoder, you go borrow a large language model, pick yours, whichever you like, Llama 2, Zephyr, whatnot. Right? Go pick your model, and the only thing that remains trainable, the only thing that you contribute in between is the so-called Q former. What does Q stand for? It stands for querying transformer. Q former is a short form for querying transformer. Now, now it's a simplification, basically. You have less to train, and it is borne out by the first. We'll read the abstract and it will make clear. So guys, it's an interesting breakthrough in the sense that it simplifies the whole training and everything. To what degree it simplifies, we are going to read through the paper and see. The cost of vision and language pre-training has become increasingly prohibitive due to end-to-end training of large-scale models. Is it true? How many of you can pre-train a model? How many of you were busy pre-training your model in the garage today morning? None of us, right? Because despite the garage culture, innovative startup garage culture in Silicon Valley, no startup sits and pre-trains models. I don't know of any. Why? Because to pre-train models, you need the kind of hardware, right, for which most likely, even if you sell your house, you still won't have the money for. It is this bad. So that statement is borne out. The cost of vision and language pre-training has become increasingly prohibitive due to end-to-end training of large-scale models. So that's the problem they're going to address. This paper proposes BLIP-2, a generic and efficient pre-training strategy that bootstraps vision language pre-training from off-the-shelf frozen pre-trained image encoders and frozen large language models. Succinctly saying what we were saying a moment ago, isn't it? Vasanti, would you mind coming this way? I'm having a hard time seeing your face. Yes, better. So BLIP-2 bridges the modality gap with a lightweight querying transformer, which is pre-trained in 2 stages. If you look at this picture, the querying transformer, Q-former, literally looks like a bridge between the two, isn't it? Which we pre-train in 2 stages. The first stage bootstraps vision language representation learning from a frozen image encoder. What does it mean? If my image encoder is frozen, BIT, whatever it is, or a clip, then what happens? I feed it text. And if I give it an image, which we know is the caption, the text is a caption for, then I can easily use my contrastive loss and align the two, isn't it? So now I got that. Suppose I keep my encoder the same. I know that this image, this caption go together. What do I need to do? I basically play the contrastive loss game and one part is taken care of. Yeah.
So something like similar to RAG, right? No.
No, don't bring in RAG. It's entirely different from RAG, guys. Please don't bring in RAG. Guys, you're bringing in RAG because you're saying that you're getting information from outside. Is that the why? Is that the reason?
Yeah, the query is coming in, and then like I'm using the pre-trained model. I'm giving a little bit of context and asking the large language model to generate a text.
No, not the text yet. The first stage, you just give it an image and a text that you know, and you say align the two. Like create the Q former changes weights and biases such that the text vector and the encoding coming from the image encoder are aligned. That's all. Right? That is all you're doing. So think about it this way. See here, image encoder produce a vector like this. In the beginning, when you have an untrained model, you give it some text, it will produce a vector like this, right? You're saying, hey, no, bend this vector and align it to this. Align it to this. Instead of this, align it to this. So that is the first stage training, right? Because it is telling you that I am telling you this text belongs to this image, right? So the two are the same, and therefore just go. So that's your first part of learning.
This text vector has no relationship to that image vector, right? You create.
Yeah, you just in the beginning you just ran. It will if you give a untrained machine, it will just produce some vector randomly, right? And then you gradually train it to bring it in alignment. The second stage bootstraps vision to language generative learning from a frozen. So the second part has to do with, remember the third and the fourth pillar on the right-hand pillars of BLIP, right? It basically says, okay, now it is good. You have the text and you have the ground, thing. Let's focus on aligning the generative part, the decoder part of it, right? So therefore what happens is inside the Q former, you'll actually see 2 pillars. The first pillar is trying to align to the encoder. The second pillar tries to align and make sure that eventually the decoder is producing the right text. Because ultimately what will happen is you're giving some signal to the decoder. And the job of the second pillar is just to make sure that the signal that goes into the decoder is such that the decoder produces the text you want to see. Okay? These are the 2 phases. The second stage bootstraps vision to language generative learning from a frozen language model. Frozen language model, think Llama 2 that you just downloaded or something like that. BLIP-2 achieves state-of-the-art performance on various vision language tasks despite having, and this word is the most important sentence in this paper, BLIP-2 achieves state-of-the-art performance on various vision language tasks despite having significantly fewer trainable parameters than existing methods. For example, our model outperforms Flamingo 80 billion parameter by 8.7% on a zero shot, some VQA, V2 benchmark, right? With 54 times fewer training parameters, practically 2 orders of magnitude smaller. Means with a much smaller model, a baby model, you are beating Flamingo 80 billion parameter. You realize the implications of that, right? So we also demonstrate the model's emerging capabilities of zero-shot image to text generation that can follow natural language instructions. Now, I will move over the paper because if you know a blip, some of the paper sort of goes over a similar territory. But here's the main method. Let's look at what it's doing. Oh, look at the inner two. You see the Q former, which is in yellow. And you see the 2 pillars there. Those are the two inner pillars of blip. Just to recap, what were the blip pillars? Let's go back to blip. Yeah, look at this. The left pillar is the image encoder. You see that, right? The rightmost pillar, pillar number 4, is the decoder. So what have you done? You have replaced the image encoder with you just borrowed an image encoder. You borrowed a LLM for decoding. And then what do? You say, okay, the in between, we paint it yellow and call it basically a query transformer. You change the architecture a little bit. It's not exactly just changing the name and so on and so forth. So you do a little bit extra and we'll see what is it that they do.
So intuitively, can think that it is reducing the training time by half.
Not just by half.
Or maybe more
huge amount.
We are not going to do that like the pillar 1 and pillar 4 training because we are borrowing that one.
That is right.
Pillar 1 like we are going to try.
Yeah. See, the biggest training times, image encoder take a long time to train. BLIP is not a joke to train. Right? Likewise, training a LLM is no joke. Right? Those 2 things you take out and you do the inner thing, improve upon this, rightly, we'll do that. You realize that you're looking at a model that is just 100 or so million parameters, 0.1 billion parameters, something like that, right? And you can train it on your machine, right? So the training cost drastically reduces. And they talk about that. And that is the core of it. So this was the BLIP paper. You see how complicated, how much is going on. If you can say anything about this architecture, you can say that, gosh, it would be expensive to train. Yeah. And then comes the next paper. And then what do? Image encoder is there. You don't see the decoder here, but basically you see the inner 2 pillars. The first pillar aligns to the encoder. The second pillar is basically ready to push something into the decoder. So let's look at this. I won't go over the paper because this image, quite often in these research papers, all the textual descriptions that you see, much of it is captured or succinctly represented by figures in the paper. So let's focus on the figures and I'll explain it to you. So let's look at this. Image encoder will produce a what? Image vector. It does that. Now, there is something new here. This is new. They found that instead of giving it text, the first pillar, it says don't give it text at all. Remember, in BLIP, you would be giving it the text. It says don't give it the text. Instead, pretend as though you're giving it the text, but actually give it some hardwired query vectors, right? Those query vectors, right, is a fixed set of vectors that are there for your engine. Like once a BLIP-2 is fully trained, is that. What it is that it will always be the input trigger to this encoder layer, to the encoder pillar. Are we together? Now the question comes, okay, what's the value of those query vectors? How do I determine? What's the answer to that? Can you guess? Let the backpropagation learn it. Right? What is a good library of query vectors? Yeah. So remember, this is not the text. You give it the query vector. That's why it's called the query former, query transformer. When people initially look at it, they often think that, okay, query is what I gave, the input. No, it is not. It is just a library of learnable vectors that triggers the first pillar. Now comes an interesting part, which I want you to pay attention to in this diagram.
I'm still confused about queries. So you're saying it's a bunch of learnable vectors?
Vectors.
Okay, how does that look like though? In this case, you're giving in a cat. So what would your query be?
Oh, it is independent of whatever input text goes. As the machine trains, what you're basically saying is that the first pillar, don't give it text, but you need to give it something. Encoder will expect some input.
So it could be some randomized vector.
Yeah. See, you could give it, initially you start with randomized vector and then let back propagation go and fix so you just treat it as weights, a vector, right, of values that let it figure out what is the best set of hardwired vectors that will essentially fire the transformer.
So it could be something I pull out of thin air, feed it in and let it learn.
Yeah, you don't, what happened, no, let's go through this. Before, when the machine learns, you just you give it random weights, right, random values. Then as the backprop happens, see, what are the things you can't change? Input and output. Input is an image and a text, output is generated text. Those two you can't change. But everything, you just say learnable queries is, if I don't make those queries to be the input, then what else can it do? And the answer is, see, I need to give it some queries because this transformer needs something at the bottom. It needs a fire at the bottom to get launched.
Can it be something constant or do I have to randomize it every time?
No. In the training process, you randomize it. So then what happens? It will back propagate and learn. You let this query vectors learn from the back propagation. And then what happens? When the model is fully trained, it just becomes a bunch of constant vectors. Right? It just becomes an internal machinery inside the transformer, inside the BLIP-2.
So at the end of this whole process, nobody will be able to guess what the learn queries.
And you don't care. The only reason they exist is it just so happens that if you look at the transformer basic architecture, right, it is encoder needs something. Remember, you used to give it text. If I can't give it text, what do I give it? And the simple answer in machine learning has always been, if you don't know what to give it, let it learn what it likes.
Is that the reason why we read in the media that, OpenAI doesn't know what's inside or how it's not doing?
Well, yeah, all neural networks are black boxes. The interpretability is a huge deal and a very active area of research. But as of this moment, it is safe to say that almost all neural architectures are, for all practical purposes, they're black boxes. We superimpose interpretability using other models, which try to see the behavior and interpret what this model is doing. And so there's a huge body of research there. Okay, guys, so that's that. Now what happens? Let's go further. So you need to trigger, so you just say, okay, whatever goes in, let it discover what it likes. What will come out of this? It will come out, because you did not send it the text. But here is something very interesting. Text actually does go in a very interesting way. You notice that this pillar, there is another pillar into which you feed in the text. This pillar. In this pillar, you're feeding in the text, a cat wearing sunglasses. Right? The caption. This goes through self-attention, right? Now you do something which is interesting. You basically ask these two, you share this attention layer. You basically say that the weights need to be the same, match. Right? So in a way, text is also going in and query vector is also going in effectively into this, but logically it looks like two different pillars. Yeah. So if you look at this cross attention, now do you notice that the image is being the cross attention? Whatever the image is coming, vector, image encoding is coming, it is the cross attention to the first pillar. Yeah. Right. And so what comes out here, see, what comes out of here and here is image text matching. Where did the text come from? The text comes from because of the sharing. Right? And the text is going in this direction. So, so what happens is here in the cross attention, image meets text meets query vectors, isn't it? All three meet there. Are you seeing that, guys? Image, text, and query vectors, they all meet. And so the output that you get here, you will get some text encoding, edge text, but it is grounded. It is image grounded text. It is not just image text encoding, because cross attention from the image has come. So it is already imbued with information or influenced by information from the image, isn't it? That's why you call it image grounded, because of the cross attention. And then you do image text matching. That's good. And then you also have your standard image text contrastive loss for obvious reasons. So those three loss function terms are there. You notice that it doesn't change the BLIP architecture. It just borrows components effectively and changes it a little bit. This query thing has come in between. The text goes in, you again do image grounded text generation. When you do the image grounded text generation, so how does it work? Let's look at the picture. This picture is very instructive. So suppose if you do this, BLIP-2 second stage vision to language generation. So suppose you have trained, let's say that the first phase is trained. You want to train the second phase in which the generative task. How would you do that? You take a cat, you feed it in here. What will come out of it? H image. Learnable queries are there. You didn't feed it any text. QFormer is going to produce a representation, isn't it? Which is image grounded vector. You take that vector, and what you do is, now you take a decoder LLM. Decoder LLM will need the data in some format, right? Some will take 1000 token with padding, 512 token with padding, whatever the shape of input vector it has. You need to transform the output of this to the input of this, whatever decoder, whatever LLM you happen to borrow. Make sense, guys? Like GPT-3, for example, is a decoder architecture, right? You need to put it there. But there's a problem. Obviously, the dimensionalities of the vector spaces will be different. Yeah. Vectors will be. So you realize that I can change dimensionality from one to the other using a matrix operation. But then you think, oh, if I'm going to do matrix operation, why not throw in the full-fledged feed-forward layer? Let there be some deformations. Let there be some learning also there. Yeah. And so what you do is you don't do a straightforward. You throw in a feed-forward, a few multi-layers right in there. While you're at it, why not? Right. So these also become learning part. So the only parts that get trained are the QFormer and the fully connected. That's the bridge between that and the decoder, right?
But isn't there a cost to converting that fully connected box into a feed-forward layer?
Yeah, fully connected and feed-forward are synonymous. They're the same thing.
No, but instead of just, is there a difference between just transforming it to a different
matrix
versus?
Yeah, see what happens is that, think about it this way. You put a weight matrix, right? You take the output of this, let's say that the output of this is A out. From the QFormer, you multiply it by a matrix to get input to the, let me just call it decoder input. You can do that. It's a matrix multiplication, right? Then you say, okay, how much does it cost to add an activation also there? You do that, you already got a one layer feed-forward network. While you're at it, you say, why one layer? Let's add a couple of layers more, right? So you can do that. Ultimately, it's a choice. Does it add to the cost? Yes, it adds to the cost. Feed-forwards add a lot of parameters to it. But generally, feed-forwards are also relatively cheap to train. You do that. See, you have already reduced the size of your model from billions of parameters to just 100 or a couple of hundred parameters. Right? A tiny model. It's not expensive to train. Likewise, if you use a full-blown encoder-decoder kind of architecture, right? So, for example, BART and so forth. So then what you do is, again, the same thing. What is the input to a full-blown transformer? You have to feed it to the encoder, not to the decoder. Right? You feed it to the encoder. And how would you train? How in the world would you train? So, for example, you can give it a picture of a cat and you can give it half the phrase. Do you see a cat wearing a sunglasses? was the caption. You give it a cat and you put a loss function and say that you better produce wearing sunglasses, right? And you train it with that. That's it. So this is your BLIP-2. Its significance is that it's much smaller. And let's look at the results, because the results are beautiful. And I don't know, when I looked at it, I was like, wow, I frankly couldn't answer half the questions. Right? Explain the advantages of this product. What does it look to you guys like? A car, but it says this Audi e-tron Quattro, whatever that thing is, I have no idea. Concept, oh, it's a concept, is a plug-in hybrid electric sports car that has a range of 310 miles and can accelerate from 0 to 60 miles per hour in just 4 seconds. Do you realize in the course of today morning, we have gone from captioning, simple captioning, to how far we have come? That's right. Let's look at the second one. Tell me something about the history of this place. You didn't tell it anything. You're asking it to understand. So where is the understanding coming from? The decoder, language, the expressiveness of the language is coming from the LLM as a decoder, right? The Great Wall of China was built in 221 BC by Emperor Qin Shi Huang to protect the emperor's capital from invaders from the north. Okay.
This one is not offering that filtering and relabeling stuff because of using the.
No, you can still use it for that. See, remember, you can always generate it and then you look at the alignment with that. So all of those properties are sort of assumed. Okay. But it's talking about what new it can do. Now, the third one, write down the facts that you know about this flower. I looked at this and all I could say is, okay, orchids. And I couldn't say anything further. And then this one goes out. It's a genus of flowering plants in the orchid family. This family, the one right here. Okay. It is native to Eastern Asia and Southern East Asia. It's a perennial flowering plant that grows up to a height of 1 meter. How many of you are impressed? It's good, right? And this is the loveliest part. Look at this. Is this photo unusual? So think about it this way, guys. You're now asking it a question. Is this photo unusual? Right? And it says, yes, it's a house that looks like it's upside down. Yeah. It's not just, how would somebody get out of the house? That's hard, right? And then it says it has a slide on the side of the house.
So
That's impressive.
where is the inference coming from?
This is it. See, think about it this way. All the ingredients are there. Do we have the ability to understand the image? The encoder part gives you that. The cross entropy loss gives you that. I mean, the contrastive loss gives you the understanding. From that understanding, do you have the ability to then generate good language? The decoder gives you that, isn't it? You put a full-blown LLM there, isn't it? Because from that understanding, now you can decode.
No, but it was actually able to solve a
Problem, yes.
It saw a slide and said, yes, you could slide on.
Yeah, yeah. So now you ask this, what are shown in the picture? A man and a chicken. What does the man feel and why? He's scared of the chicken because it's flying at him. Right? He's literally chickening out. So the next is, what are the ingredients I need to make this? You realize that this takes some understanding, right? It needs understanding of the image. It also needs understanding of enough world knowledge. Is a scare? No, we are getting into pretty deep territory. If you think this is the scariest that AI has achieved, wait, we are only midway through the course. Pepperoni, mozzarella, cheese, pizza sauce, olive sauce. So do you realize how far we have come? Some of you were asking, what if the captions are not good? who was asking in the morning, and I asked you to wait. Now you know why. Yeah, now you know why. Okay, what is the first step in making this? Yeah. Yeah. Now let's go to the next one.
I had a question on
Mhm.
house picture. So here, I mean, could the model have said that your data is wrong because you have fed the picture which is upside down?
No, it's not upside down. It knows it's not upside down.
I know I'm saying, but if, assuming it was a real picture that was flipped upside down in that case, I guess would that consider model will say that this is wrong data or this? I mean,
Actually, I don't know. Somebody told me that this actually is a real one. This is a real picture. Somebody told. I don't know if it is true. Somebody for fun built something like this.
Yeah, and it's interesting that the model accepted that, saying that yes, it is a real house upside down, and it's not a wrong inverted image.
It's not an inverted image. You can see, right? You can see the support pillars here. Do you see that? They're holding it up in an angle.
You can also see the grass on the ground.
Yeah, and you can see the grass on the ground, and the trees are upright. The sky is in the right place.
Turns out there are a bunch of upside down homes in the net.
There are, huh?
Yeah.
Oh, yeah. So there you go. They're upside down homes people have built. Okay. Which city is this in Singapore? What do you think? Why do you think so? The city has a statue of a merlion. So this is Singapore. Actually, I would have said the three pillars because this building, as you know, if you've been to Singapore, is iconic.
Yes.
I actually know some people who were in the construction of it. And at the top of it is a beautiful swimming pool. You can actually swim across the three buildings in the swimming pool. Yeah, Mridul, you've been there, is it?
Yeah.
Oh, nice.
The high end is a very.
Yeah. It's a very iconic thing. Of course, it wouldn't be it wouldn't be complete without this picture from Titanic. What happens at the end of this movie? The answer is laconic. The Titanic sank. So, that's so depressing. Did Leonardo DiCaprio's character survive? He drowned. What is in the photo? A pizza that looks like a cat? Or what is the nose made up of? A slice of pepperoni. It figured that out. Imagine its level of understanding. Right?
I really want to know the reference data that was used to
No,
generate
there's
this
nothing
data
magical.
plan.
See, there's nothing magical. I'm telling you, math is the magical thing in the world, right? There's somebody once said something very deep. One Indian philosopher said that the most magical things, right, are hidden in plain sight. Right? If you really think about it, all the magic is right in. If you think of math, for example, everywhere you look, there is math. You know, you throw a pebble in the water, you see sine waves, right? Its amplitude are probably Legendre polynomials, right? Legendre function. You look at the cable of the Golden Gate Bridge, you see mathematics there in the right. Am I right? Anybody from civil engineering here?
I'm not saying it's magic, but this is like at the level of a lot of even more than humans.
No, all it means is that the human evolution or the biological evolution ultimately is made up of very simple ideas. Nature has followed simple mathematical laws. That's all it means. And it is true. I mean, at the end of the day, I believe that the entire universe is a mathematical construction. So some people believe that the universe is filled with God. I believe universe is filled with math. No, I'm kidding.
So, studying history, these kinds of stuff is going to be like all this studying of anthropology and these kinds of stuff came from the fact that a human, based on reading lots of text, a human is able to correlate and inference from it, right? All that will be gone with this.
No, all it means is that we can create intelligences that are not of biological origin. We're getting there. Some specialized intelligence. We don't have generalized intelligence, but we have. See, any specific task, like not any, quite a few specific tasks, machines do better than us. So I'll give you an example. It's a bit of a digression. We recognize things in the blink of an eye, instantly. Machines, even today, like this will go through the whole inferential layer and get it. Because the human eye has gone through, even fishes had eyes. There's at least a few 100 million years of evolution there. But look at our ability to reason. It probably has a history of what, about 100,000 years at most, right? Since we reason. And you can see how poorly developed reasoning is in most human beings. Right? Most people can't reason straight. I mean, most of us will make mistakes and then we go review our stuff. I make a lot of mistakes. I go review. I can't do anything right without revision. Right? So reasoning is obviously, it is immediately obvious. I'll never mistake a tiger for a house, right? But when I'm reasoning through and doing math, I will make mistakes. My pluses will become minuses, and then I'll go back and fix it. I write code and I'll have little mistakes, and then I'll have the IDE help me fix it. So reasoning, we are very poor reasoners, but machines, it turns out, are very good at reasoning. Or they're getting better and better at specialized reasoning. They still can't reason the way we do. We are still superior at much deeper reasoning, but for simple things like this, they do very well. So, here it is.
Asif,
Hey, yo, bro, look at this. Bro.
Go ahead, Sarah.
Kaden, quiet. Don't need to yell.
Hey,
Asif, I was going to make a comment on the Titanic situation. The first question, where the question is, what happened at the end of the movie? Okay. In fact, if I think the end of the movie was not the Titanic sinking. There was more to that after in that movie. And that's the scary part for me, where it got the core of the movie and it got the, and to say that the Titanic sank is the scary part for me. And I don't know, where would a machine be able to get to that level of information?
That it is good at. See what happens. You're right. In the Titanic, there was an epilogue. There was a scene in which the lady goes back to the place of the Titanic and throws that whatever precious jewel or whatever she's wearing into the water. And the guy who was searching for it, poor guy. But right. But this is a power of machine. That's why people like Jeffrey Hinton believe that these machines understand. Because it could tell that even though that was the factual end, that was actually an epilogue to the story. The story ended with, well, the Titanic sinking and the main protagonist dying.
Or it could be possible that it's textual understanding of the stories.
Yeah, that's right. That's the other point of view. You could say that all it knows is a stochastic parrot. It's just pumping it out, right? The most plausible sentences. So you don't know. We don't know. The trouble is we don't know these things. At the moment, all these things that we are building for the first time, you build a watch, you know exactly how it works. You build a car, you know exactly how it works. You build a F-35 fighter pilot, a fighter jet, marvelous piece of machinery that taxpayers pay billions of dollars for just one piece of it. And yet we know what it is doing. Every part what it is doing. But you build a large language model and you have no idea how in the world, and to what extent it understands, to what extent it just regurgitates, to what extent it remembers, we have no idea.
So, in this conversation, so does it mean that it has some kind of a memory? It's keeping track of the questions before? Relating to these questions?
See, LLMs generally try not to. Because, I mean, see, if you use the API, it's memoryless unless you do a chat, a conversation. You remember it, right? So what happens is, if you go to ChatGPT, it remembers the track history of the previous conversations. And then it uses that as a context to answer the next question. It keeps appending it as a context.
That's what's going on here.
Yeah, that's quite likely. Now, Then it says, write a romantic message that goes along with this quota. So this is a sign of things to come. Love is like a sunset. It's hard to see it coming, but when it does, it's so beautiful. Okay, there you go. Now I'm told that the young people, there's something very interesting is happening. One of the most searched for things or uses of the LLM is to young people, they say, what is a good opening line? I'm going to meet a girl. What's a good opening line? Right? Give me some really nice thing to do. What should I say? This is the person, and what should I say? So apparently, the LLM seems to have become the machinery for dating.
That's very useful.
So there you go. Tell us about the photo you took of Darren and Blah. Yeah. And this is so anyway, I won't go more into it. The results are pretty impressive and they speak for themselves. Now, I won't have time for the lava paper. I'll cover it perhaps on Wednesday. Oh, look at this, a few more. These are the incorrect examples for instructed zero-shot image to text generation using BLIP-2 with blah, blah, blah. Write a famous quote said by this person. And it comes up with, it just makes it up. But that says more about the state of the art of the LLM than about this particular thing. Yeah?
Finally, human one.
Finally, humans won. Yeah, if you want to think like that. Right.
So, but you can go back to the previous, maybe the one before that.
I wouldn't say humans won there. Maybe there was a human at some point in time made that mistake and told the machine that.
Yeah. So the last row, the middle image.
Middle image.
Yeah, it has the name of the people.
No, because you give it in the input. See,
Okay.
you gave it here. Yeah.
Albert Einstein example.
Mhm.
I mean, when compared to many of these, that seems pretty simple, straightforward. Identify the person, figure out.
No, you're saying give a quote from this person because the LLM just hallucinated and cooked up something. So if you think about this quote, right, it looks very Einsteinish. It looks philosophical, Einsteinish, something Einstein may have said, but he actually didn't. The quote is from a different person. Right. So this is more about the LLM limitation rather than this Q form stuff. BLIP-2. Can I wear this for my trip to Canada in December? It missed out on the weather part, right? Right. Likewise, you give it a iPhone, then it turns out that LLM was not updated to recognize this thing. This is iPhone 14, which apparently is recent. So,
going back to the pizza example, looks like it's all talking about sort of pepperoni. Probably it's not been trained with vegetarian pizzas, maybe not that flavor at all.
See, look, I can easily imagine. See, imagine, guys, most of the people sitting in grad school are living on soda and pizza and coffee. When I was in grad school, I was told that graduate students are machines who convert coffee into theorems. So,
actually, like in this picture, there's a lot of pepperoni embedded on the pizza.
okay. All right, guys. So, what I will do. Yeah.
When you look at this term cross attention, like in the figure 2, the cross attention would simply mean that it's the image and the text that you're trying to
make them pay attention to each other. Exactly. The tokens of one pay attention to the other. That's all it is. That's all it is. Yeah.
They give the models they use.
Yeah. Beautiful, isn't it? It's a very simple idea. You simplify BLIP to this, and you get more for it because now large language models have become very powerful. And you just say, let's take the state-of-the-art image encoder and go with that. So, all right, guys, this is the end of the theory part, and we have taken longer than I thought. It's almost going to be 4 o'clock. I would like to walk through some part of the solution to give you guys some guidance about how it works. 5 minutes break, and then let's regroup.